Hi everyone, and welcome to a new episode of Coding Adventures. Today we're going to be exploring the game of chess. Let's begin simply by creating the chessboard. So we'll need two loops for the x and y axes, or files and ranks if you prefer. And to tell if a square should be colored light or dark, we can just check whether or not the file plus the rank is divisible by 2. Let's try running this code, and here we have our very humble beginnings. I expect I'll be staring at these 64 squares a lot in the coming days or weeks, depending how challenging this turns out to be, so I'll tweak these colors to something a little easier on the eyes. Next we'll need some pieces, and I found this nice design online, which came along with some interesting additional ideas for a giraffe, a zebra, whatever this is, and several more. I think chess is confusing enough as it is though, so I'll stick to these for now. We then need to represent these pieces in code, so I'll assign each type of piece a number, along with a number for white and black. These values could be pretty much anything, but I chose these particular ones so that if we look at a piece in binary, the 3 bits on the right will tell us what type of piece it is, and then the 2 bits on the left tell us if it has a color associated with it, which can be white or black. So let's now create an array of 64 numbers, which will be the computer's internal representation of the chessboard. These are all 0 by default, but we could place, for example, on square 0, a white bishop, and on square 63, a black queen, and whatever else we want. Behind the scenes, I also added some code for actually displaying the pieces. I'm not sure if they're obscuring quite enough of the board at the moment though, so let me fix that. Perfect. Now, instead of setting up the board piece by piece in that array, I'd like to support the standard notation called fen. Here's an example of a fen string, which might look terribly cryptic at first glance, but it's actually really simple. We start at the top left square, and here we have 7 empty spaces followed by a lowercase k, meaning there's a black king hiding in this corner. We then go to the next rank and skip 3 spaces, and here we have an uppercase n, meaning a white knight. You're probably getting the idea already, so I'll spare you the tedium of going through the rest. I've written up this little function to translate those fen strings into the format we're using, and up at the top here, I'll write out the fen for the starting position, so we can load that in. And here it is. I've also implemented some simple drag and drop behavior for the pieces, although it's not quite behaving how I'd hoped. I'll go ahead and fix that quickly, so now it's making the pieces disappear for some reason. I'm rapidly losing faith in my ability to code anything, but I have at last got it working, and I think it's looking nice. Although, of course, nothing's really stopping me from sneaking in a move like this when my opponent's not paying attention. So the first real challenge of this project is going to be calculating what the legal moves are in any given position. So, these are the indices of our squares, and from any square we can move orthogonally like a rook by adding these offsets, and diagonally like a bishop with these offsets. I'll write out those values, and then I'm going to make another little array, and when the program starts up, it's going to quickly calculate the number of squares to the edge of the board, starting from each different square and going in every direction, just so we can easily look up that information when we need it. Let's then define a little structure for holding a move, and that will just record the starting square and the target square of the piece we want to move. We can then make a list of these moves and a function for actually generating them. What we can do in here is just loop over all 64 squares and see what piece is on each square, and we're only interested in the piece if it's the right color for whoever's turn it is to move. Let's focus for now on the long-range sliding pieces. That's the bishop, the rook, and the queen. So in this sliding piece function, we can loop over the 8 different directions, and for each direction we'll also have a loop for the number of squares that exist in that direction, up to the edge of the board. Now of course, our movement might be blocked by one of our own pieces, so let's skip to the next direction if there's a friendly piece in the way. Then we can create the move going from the start square to the target square, and add it to the list of possible moves. Finally, if there's an enemy piece on the target square, we'll be capturing it, so then we can't go any further than that, and we'll need to skip to the next direction there as well. This should work for the queen, which moves in all 8 directions, but if it's a bishop, we only want to look at the last 4 directions, or if it's a rook, then just the first 4, so I've added some logic here for handling that. If we now try this out on the board, the sliding pieces should all be obediently obeying the rules. I then spent some time carefully implementing the rules for the remaining pieces, but I'll spare you a detailed account of that. So at long last, the knights are free to leap about, we can push the pawns, and I've even got the hottest new moves from the 15th century like double pawn pushes and en passant.
Sacre bleu! Invader!
Pawns can also become queens, or knights, bishops and rooks if they prefer, and we can castle the kings. The only thing not yet implemented, and it's kind of important, is the concept of check. Right now, if the king is under attack, you can just ignore it, so the moves at the moment are what's called pseudo-legal. The easiest way I can think of for fixing this is a little gross, but it's to take each pseudo-legal move, play it on the board, and then look at all the opponent's responses. If any of those responses is a capture of our king, we know that our last move must have been illegal, and in that way we can filter through just the legal moves. Let's put this to the test quickly. So here, for example, if I try move one of black's pawns, we can see it has no legal moves. If I select the knight though, we can either block the check or capture the queen. So now that we have legal moves, let's create our first adversary, one who plays moves completely at random.
Round 1. Fight!
Okay, it turns out that playing randomly is not really a viable strategy. Just for fun though, let's pit the computer against itself. Truly a beautiful game. Now, I'd like to get the computer playing a lot better than random, of course, so experienced human players rely heavily on pattern recognition and intuition, and even when calculating concrete sequences of moves, they only really consider a tiny fraction of the possibilities, with most being subconsciously rejected as irrelevant. Programming a computer in this way is not easy. Instead, we want to play to the computer's strengths by crunching millions of possible outcomes. To do that though, move generation needs to be pretty speedy, and mine is the exact opposite of that. So much time rolled by as I mashed away at the keyboard trying out different ideas and of course fixing the seemingly endless supply of bugs I created along the way as I tried to speed up the move generation so that my computer would be able to look further into the future. One of the things I did was take this old code for filtering out illegal moves and throw it away. Instead, I'm now keeping track of all the squares that the opponent attacks, so we can easily detect if the king is in check, in which case it either needs to move to a safe square, or some other piece needs to move to one of these orange squares to resolve the check. Of course, this knight, for example, could block the check, except that would reveal another attack on the king from this bishop. So I also calculate these lines for limiting the movement of pinned pieces. Along with some other optimizations like keeping track of where all the pieces are instead of having to loop over the entire board to find them, I was able to speed things up a decent amount. Now, I've been moving pieces around for a while and it seems like everything's working correctly, but it's possible I've missed something, so I'd like to set up a little test. Let's write a function that gets all the legal moves and one by one makes them on the board. It then recursively calls itself, so that for each move it makes each of the opponent's responses, and so on to infinity, or more realistically until my computer runs out of memory and crashes. To circumvent that, I'll add a depth value that decreases with each call, and when it reaches 0, we'll stop going any deeper. What this function is going to do is simply count the number of positions that are reached after a certain number of moves. For example, here's what it looks like with a depth of 2 ply, which just means 1 move for white and 1 move for black. The result, if I speed this up quickly, is 400 positions. Let's run this for a couple different depths, and we can see the number of positions grows very rapidly, with almost 120 million possible positions after just 3 moves for each side. Now, what we can do is compare these numbers to the consensus that's been reached by other chess programmers, and it seems to match. But obviously there's a lot of scenarios that can't arise so early on in the game, so let's try it out on this test position, which I came across on the chess programming wiki. Okay, fingers crossed. So something in my code is wrong. What a surprise. To try figure it out, I'm going to enlist the help of one of the best chess engines out there, Stockfish. I'll enter the test position here, and then I'll ask it to run the same performance test. The fish of course gets the correct result, but what's super helpful is it gives this breakdown of the number of positions after each move, which I can compare with my output to quickly trace exactly which moves my program is getting wrong. The mistake I made involved castling, which surprised me because I'd so carefully followed all the little rules, like if a rook moves then you lose the right to castle on that side, even if it returns to its original square. But in this position, if black captures the rook, I didn't think to count that as the rook having moved, and so my program came up with this creative response. Another position that caught me out was this one. Here the pawn is pinned to the king by the rook, and so it's unable to move. But if I make some other move, and black then pushes this pawn 2 up, that breaks the pin and now the pawn is free to move again. Let me undo that move though, because there's also that sneaky en passant rule, where a pawn that moves 2 squares can be captured as if it had only moved 1 square. So that works, but in this case that reveals the attack of the rook again, and so the move is actually illegal. With those fixed, it's now passing all the tests I've thrown at it so far. It's still slower than I'd hoped to be honest, but I think it's time to start working on a more challenging opponent. There've actually been some breakthroughs fairly recently in the exciting world of chess programming, involving techniques like neural networks and Monte Carlo tree search, which I'm very curious to learn more about, but for now I'm going to go with a more old school approach. Let's begin by making an evaluation function to try gauge how good a position is. To do this, we can decide how much each type of piece is generally worth, so knights and bishops are probably worth about 3 pawns each, a rook is worth a little more, and a queen is somewhere in the vicinity of 2 rooks. We can then add up the value of each side's pieces like so, and what we'll then do is subtract the one from the other to end up with a value that's 0 if the position is equal, positive if the side whose turn it is to move is doing better, and negative if the other side is doing better. Obviously there's much more to evaluating a position than simply counting the pieces, but this seems like a decent place to start. We can now write a little search function, which should look familiar because it's the same idea as that move generation test we did a few minutes ago, but instead of counting the number of positions after however many moves, it's going to evaluate those end positions. We should also account for the fact that if there are no legal moves available, then it's either checkmate, in which case we can return negative infinity because what could be worse than losing a game of chess, or it's stalemate, which gets a score of 0. Now we want to keep track of the best evaluation, so over here we can see what evaluation each move leads to, and this negative sign is very important because a position that's good for our opponent is bad for us, and vice versa. Let's visualize quickly what's going on. So say it's black's turn in the current position, and we're trying to choose between 3 possible moves. To do that, the search will look at white's possible responses to those moves, and evaluate the resulting positions. Obviously, we could search deeper than that, but let's keep things simple. So these 3 positions will be evaluated first, and from that we can see that white should make this move, which gives a score of 6 in white's favor. Then these 3 will be evaluated, and white's best option is this move, and finally these 3 are all in black's favor, but this move is white's least worst option. So in the original position we can now see that black should play this move to ensure an advantage even if white makes the best response. Now there's a trick for speeding this up if we rewind to this moment. Here we've just evaluated a position that's good for white. In fact, it's even better than what white was able to get over here. So if you think about it, that actually already rules out this move as an option for black, and so we can take out our garden shears and prune this branch from the tree, not wasting any more time on it. This optimization is called alpha-beta pruning, and it gives the exact same results as the pure search, just faster. How much faster depends on the order of the moves, because if by some misfortune they happen to be ordered from worst to best, we can't prune anything at all. Essentially, the more good moves are searched early on, the more branches will be pruned and the faster it will be. Obviously, we don't know in advance which moves are good, that's the entire reason we're doing the search, but we can make some guesses. For example, if we're able to capture a piece of high value, say the opponent's queen, with something of low value like a pawn, that's very likely to be a good move. Also, promoting a pawn is usually a good idea, whereas moving a piece to a square that's attacked by an enemy pawn is usually going to be a bad idea. So let's try all of this out on this test position. I've set it up to search to a depth of 4, so it's looking ahead 2 moves for each side, and with just the pure unoptimized search, that took a little over a second, and it had to evaluate about 3.5 million positions. I'll now go back and try this again with alpha beta pruning enabled, and this time it finished in under 1/4 of a second and only evaluated about 500,000 positions for the exact same result. Let's do this one more time, now with the move ordering optimization enabled. This has brought it all the way down to 25 milliseconds, and it only had to evaluate about 5,000 positions this time. I actually wasn't expecting it to be quite that effective, so that's really cool to see. Anyway, it does play a lot better than random now, but still pretty terribly. The trouble is, when it reaches the maximum depth of the search, it adds up the pieces to see who's ahead, but of course that could change on the very next move if there's an unprotected piece somewhere, so it's catastrophically misjudging almost every situation. The fact is, our evaluation function is only going to be remotely reliable if no piece can be captured on the next move. So, in our search function, instead of just evaluating once the depth is reached, we can start a new search that looks only at captures, and just keeps going until no captures are left. Here's what that function looks like. It's very similar to the regular search with a few small tweaks, like of course we're now only generating capture moves, and there's no depth limit anymore. It might be a good idea to include checks as well in this function, but I'm not going to worry about that for now. Just to get a better feel for what's going on, here's the position we had earlier, and here are some examples of positions that were evaluated during the original search. As you can see, there are captures possible all over the place. With the addition of that secondary search though, the final positions being evaluated now have no immediate captures available, so hopefully the evaluations will be a lot closer to the truth. Now, there are still many aspects of the game that the computer is completely hopeless at. For example, here's a position with a lone king versus 2 rooks, which is of course easily winning for black. The trouble is, the computer can't see far enough ahead to find a forced checkmate, and there are obviously no pieces it can try win, so it just shuffles around aimlessly. So, I've added this little function to the evaluation script, which just favors positions where the opponent's king is close to the edge or corner of the board, because it should be easier to deliver checkmate there. And it also incentivizes moving the king closer to the opponent's king to help cut off its escape routes and assist with the checkmate if necessary. This only really applies to the endgame though, so this value increases in significance as the opponent has fewer and fewer pieces remaining. Let's see if this actually helps. So black has used the rook to cut me off, and has now brought the king a little closer. Now a check to force me to the edge, and that's already checkmate. I'll make it a bit harder by removing one of black's rooks, so now the computer will actually need the king to deliver mate. Let's see how the machine goes about this. It seems to be doing a very good job of forcing me to the edge, and now a clever little retreat with the rook, and it's mate once again. Let's try something different. Here black is up a queen, but I'm on the verge of creating a queen of my own. So black gives a check, and my fear is that it will just keep giving checks forever and end up in a draw. But actually, it does seem to be maneuvering the queen closer and closer to my king, and now it lands on a very important square, because I can't move the king away here or else I'll lose my pawn, so I'm forced to step in front of it, blocking its stream of promotion. Now the black king has a moment to creep forward, and when I move away to allow the pawn to promote, black will hopefully lead me on this unpleasant little dance again, where I'll be forced to step back in front of the pawn, and this should continue until the black king is close enough to help deliver checkmate. So this seems to be working, and I think it's really cool that that simple tweak to the evaluation function enables it to solve quite a variety of endgame positions. Of course, there's still many more complex ones that are beyond its abilities at the moment, but this feels like a good start. Here is an example of a much more complex endgame. White is winning, we just need to sneak our king into black's half of the board to gobble up some pawns. This is easier said than done though, because playing this against Stockfish here, you can see that black is able to block our king from entering, and if we head over to the other side, we'll find our attempts thwarted there as well. The truth is that after my very first move, the position was already unwinnable. White needs to find a very precise path, starting with this move, to outmaneuver the rival king. To solve positions like this, our program needs to be able to look very far into the future. So let's consider the concept of transpositions, which are identical positions reached by different sequences of moves. Currently, we're wasting a lot of time searching and evaluating these identical positions when we could just store the result of the position the first time and look it up if we encounter it again. Now, we can look up positions based on their fen string, of course, but these are relatively slow to generate and compare, so instead I'm going to use a technique called Zobrist hashing, which is just a quick way of generating a single number to represent a position. I'm using a 64-bit number, which means there are over 18 quintillion possible values we can have, which sounds like a lot, but that's peanuts to the number of possible chess positions. So with this approach, we do run a risk of looking up an evaluation and unknowingly getting the result of a completely unrelated position. What we can do about this is pretty much nothing. If we want the speed, we have to live in fear. It should be pretty rare though. So let's go back to this endgame position, and I'm going to play the black side now against our little AI. I'll give it 1 second to think, and it has found the correct starting move at least. I hope this is going to work, because the hashing and transposition lookup stuff was a real headache to get working, and I'm pretty confident there are still some nasty bugs lurking in my code. Anyway, I need to block the white king from entering on this side, but our opponent has managed to orchestrate it in such a way that I believe I'm going to be too late to prevent it from sneaking in on the other flank. I think it's doing a really good job here, so now while I'm distracted with this pawn, it's heading back over to the other side to eat up my other pawns. I suspect this wasn't the fastest way to finish things off, but it should definitely do the trick. My last faint glimmer of hope is to get this pawn storming up the board, but it's just too far behind in the race, and I think the computer's going to be able to cut it off pretty easily. I am getting very close to promotion now though, so it needs to be careful. Oh, it actually doesn't care. I guess if I make a queen it'll simply checkmate me over here. I have one last trick up my sleeve. I can promote to a knight, checking the king, but it just steps aside, and now there's really nothing I can do. Very cheeky behavior from the computer. Okay, so I'd say the most glaring weakness now is the computer's opening play. It just shuffles pieces around, because even with all the optimizations we've done, it can't see nearly far enough ahead to know that this will get it into trouble sooner or later. So we need to encourage it to put its pieces on reasonable squares, and a simple way of doing that is to create a little map of bonuses for each square for the different pieces. Here's one for knights, for example, tempting them towards more central locations where they can control a lot of territory. And here's one for the king for the early and middle stages of the game, suggesting that it shouldn't wander too far from home, and that it might find the most safety towards the outer edges of the board. Obviously, these maps are very generalized, and good squares will depend on where your other pieces are, and of course where the opponent's pieces are, and so on, but this should be a helpful nudge in the right direction at least. To test this out, I'll try making some opening moves again, and it seems to be responding a lot more sensibly now than it was before. It's bringing out pieces and taking some sort of control in the center, so that's very nice to see. Now, it will respond the exact same way every time, which is a little dull, so to inject some variety, I've downloaded a bunch of Grandmaster games, and for the first 5 or so moves, I'd like the computer to pick a random move from these games to play, if it can find the current position in there, of course. This collection of games is pretty small, there are only about 8,000 or so in here, but it should be enough for now to give a decent variety of options, at least in common opening variations. Alright, now I set myself a deadline for this project, which I've actually already exceeded by several weeks. It turns out chess programming is quite the rabbit hole. So even though there's a million things I still want to do, I'm going to stop adding stuff, at least for now, and let's finally play some games to see how good our little adversary has become. So Black has played the Nimzo Indian, and I never really know what to do here. I'm gonna try this. It's a bit of a strange looking move, but I saw it recommended in a video by Grandmaster Daniel Naroditsky, so if this goes badly, I at least know who to blame. Actually, I think I'm already messing this opening up, to be honest, but the computer is out of its opening book now, so it'll have to figure things out on its own as well. I should probably focus on getting my kingside pieces developed so that I can castle to safety. Let me just capture here quickly first and defend my knight.
Thank you for a very enjoyable game.
So as I try to take my revenge here, I want to talk about an interesting problem that I glossed over earlier. The problem is, how do we decide what depth to search to? Because obviously we want to search as deeply as possible, but we have to take time constraints into account. Now, it's impossible to predict how long a search is going to take, and if we stop the search before it's finished, the results will be pretty meaningless because it won't have considered all of the opponent's responses yet. When I was researching this problem, I was initially a bit horrified by the solution I came across, but it's actually really clever. It has a slightly scary name, iterative deepening, but the idea is super simple. We first do a search to a depth of 1, and when that's complete, we then do a search to a depth of 2, then 3, and so on. So this way we can of course interrupt it at any time, and just use the result from the last fully completed search. The reason I was horrified though, is that each time we start a deeper search, we're redoing the work of all the previous searches we've done. It seems like a huge waste of time, especially because we can't even use all the evaluations stored in the transposition table, because they're not helpful if they come from a shallower search than we're currently doing. But, and this is a big but, remember that with alpha-beta pruning, if we look at good moves first, it will be able to prune more branches. And so what we can do is keep track of the best moves during each search, and look at those first in the next deeper search. The deeper search won't always agree that those are good moves, but a lot of the time it will, and it turns out that the increased amount of pruning that this leads to means that counterintuitively, the iterative approach is often even faster than just doing the whole search once. I'm not sure if that explanation made any sense, but I hope so because I thought this idea was really interesting. Okay, so I've played a bunch of games behind the scenes by now, and I'm able to win most of the time, so the computer obviously has lots of room for improvement in all aspects of the game, but I think there are two main weaknesses. The first is its very poor understanding of king safety, which means it often thinks it's doing fine, and then suddenly realizes it actually needs to start sacrificing pieces in order to stave off checkmate. The other is its understanding of pawn structure, or rather the total lack thereof. It likes to advance pawns up the board to try promote them, but it has very little ability to judge if a pawn is weak or strong, which causes it to happily go into a lot of really bad positions. So I'd like to come back to this project at one point to try address these issues and hopefully make it a much more formidable opponent. But I think this is an okay start, and I definitely had a lot of fun working on it. So thanks for watching to anyone who might have made it this far. I know it was quite a long journey, but I hope you found it interesting. Until next time, cheers.